In this module, we will start with the basic concept of homogeneous, homothetic and monotonic function. We can briefly explain that the convexity function y is equal to fx that is defined and continuous on interval x is called convex if for any a and b from x and numbers q1 and q2 such that q1 plus q2 is equal to 1, q1 is greater than 0, q2 is greater than 0, we have that f bracket open q1a plus q2b bracket closed is less than q1fa plus q2fb. Concavity function y is equal to fx that is defined and continuous on interval x is called concave if for any a and b from x and numbers q1 and q2 such that q1 plus q2 is equal to 1, q1 is greater than equal to 0, q2 is greater than equal to 0, we have that f bracket open q1a plus q2b bracket closed is greater than equal to q1fa plus q2fb. Quasi-concavity. A function fx mapping from the reals to the reals is quasi-concave if it is non-decreasing for all values of x below some xo and non-increasing for all values of x above xo. xo can be infinite or negative infinite, that is a function that is everywhere non-increasing or non-decreasing is quasi-concave. Quasi-convexity, a real valued function defined on a convex subset is said to be quasi-convex if for all real the set is convex. This is equivalent to saying that is quasi-convex if and only if its negative is quasi-concave. After studying this module, you shall be able to know the concept of concave and convex function, identify the given function as concave or convex, identify quasi-concave and quasi-convex function. Draw a graph of quasi-concave and quasi-convex function. Understand the advantage and disadvantage of quasi-concave and quasi-convex function. In this module, we are going to study concavity, convexity, quasi-concavity and quasi-convexity. Before starting this module, it will be beneficial to define some of the concepts that will be used frequently. The first being homogeneous function. It is a function that has multiplicative character. That is, if an argument is multiplied by a factor, then the result will be the sole power of the factor. For example, let the production function be q is equal to k into 5, L into 5, which is equation 1. If both k and L multiplied by a factor a, then the result will be q is equal to a1 bracket open in k into 5, L into 5, which is equation 2. That is, equation 1 is homogeneous of degree 1. It should be noted that homogeneous is a cardinal property, not ordinal. Homothetic function. A function is called homothetic if it is monotonic transformation of homogeneous function. Monotonic function. Monotonic function implies more is better in the preferences. A function is monotone if for all x, y which is element of a positive natural number. X is greater than equal to y, that is y is moves towards ux is greater than equal to uy. A function is strictly monotone if for all x, y are the element of all positive natural number. X is greater than y, which moves towards ux greater than ux. Convex set. A set U is convex set if whenever x and y are a point in U, then every point on the line segment joining x to y is in U. That is, axy is equal to bracket open tx plus 1 minus ty, t lies between 0 and 1. Now we shall discuss concave and convex function. A real value function f defined on convex set U of Rn is concave if for all x, y in U and for all z between 0 and 1. Function of zx plus 1 minus zy is greater than equal to zfx plus 1 minus zfy. A real value function d defined on the convex subset U of Rn is convex if for all x, y in U and for all t between 0 and 1. G bracket open tx plus 1 minus ty is less than equal to tg x plus 1 minus tgy. Geometrically, a function is convex function if a line connecting 2 points on the graph lies above the graph. This can be explained with the help of a diagram. A function is concave if and only if the line connecting 2 points on the graph lies below the graph. This can be explained with the help of a diagram. Now we will analyze how test of concavity and convexity is done. Till now we discussed that how to identify whether a function is concave or convex by looking at the graph. If a line segments join 2 points on the graph lies above the graph, it is called convex function, and if the line segment join 2 points on the graph lies below the graph, it is called concave. But sometimes it is very difficult to draw a graph of a function. Therefore, it is necessary to develop the analytical criteria for the identification of concave and convex function. Analytical criteria for concavity. A function fx is concave in a particular interval if and only if its first derivative f prime x is decreasing function of x in a particular interval. A function fx in a particular interval is concave function if and only if its second derivative f double prime x is less than equal to 0. In other words, a function which is twice differentiable will be a concave function if the second derivative is less than or equal to 0, that is f double prime x is less than equal to 0 on all points of its domain. Example, let output Q be produced by only labor L and production function is given by Q is equal to L raised to the power of half. Differentiating equation we get dq by dl is equal to half L raised to the power of minus 1 by 2, which is greater than 0. Strictly concave function. If a function can be differentiated 2 times, then that function is said to be strictly concave if its second derivative is less than 0. That is, f double prime x is less than 0 on all points of its domain. Sometimes second derivative of a function is negative, sometimes it's positive. This type of function is neither concave nor convex everywhere, but this function will be concave and convex in a particular interval. Example, let the function be fx is equal to minus 1 by 3x cubed plus 3x squared minus 5x. The first derivative of the function is f prime x is equal to minus x squared plus 6x minus 5, and the second derivative function is f double prime x is equal to minus 2x plus 6. That is, f double prime x will be greater than 0 if x is less than 3 and the function is convex in this range, and f double prime x will be less than 0 if x is more than 3, hence the function is concave. Moving on to features of concave function, there are 3 basic properties of concave function. The critical points represent global maxima. Weighted sum of concave function is concave. The level sets just have the right shapes for consumption and production theory. Now we will study advantages of concave function. The concave function represents global maxima, which is very important concept of economic theory. For example, profit maximization, cost minimization, utility maximization is only possible when these functions are concave. And the third advantage is indifference curve and isoquant drawn on concave function is convex from the origin. This is shown in the diagram. Another advantage of concave function is that they behave well under addition and scalar multiplication by positive number. This can be explained as follows. Suppose that f1 to fk are concave function, each defined on the same convex subset. Let b1 to bk are positive number, then b1 f1 to bk fk will also be a concave function. Convex indifference curve from origin represent diminishing marginal rate of substitution. That is, if consumer wants additional unit of good 1, then she will sacrifice less and less unit of good 2, and this property is very important for consumer and production theory for optimization. Example of concave and convex function. Suppose a single input I is used to produce Q. Prove that if production Q is equal to 1 divided by 3, where I is greater than 0, then cost function CQ is convex, whereas production function is concave. Solution. Production function Fi is equal to I raised to the power of 1 by 3. The first derivative F prime I is equal to 1 by 3 raised to the power of minus 2 by 3. The second derivative F double prime I is equal to minus 2 by 9 raised to the power of minus 5 by 3 is less than 0 if I is greater than 0. Therefore, the production function is concave. The cost function is Ci, which is equal to alpha plus beta I, where alpha is fixed cost and beta is marginal cost. Since Q is equal to I raised to the power of 1 by 3, therefore I is equal to Q cube, substituting in the cost function in terms of output. CQ is equal to alpha plus beta Q raised to the power of 3. First derivative of cost function C prime Q is equal to 3 beta Q squared. The second derivative of cost function C double prime Q is equal to 6 beta Q greater than 0. Therefore, cost function is convex. Convex function. A function is said to be a convex function if it is twice differentiable and f double prime x is greater than equal to 0 at all point on its domain. Example, fx is equal to x squared. The second derivative of this function is f double prime x is equal to 2, which is greater than 0. Therefore, it is a convex function. This can be explained with the help of a diagram. Now let us understand quasi-concave and quasi-convex. As we have discussed above, concave functions have cardinal properties. In other words, it depends upon the number which functions assigned to the indifference curve and isoquant. Whereas quasi-concave function is ordinal version of concave function, we can also say that any monotonic transformation of concave function is quasi-concave function. All convex functions are also quasi-convex, but not all quasi-convex functions are convex. Example, first, the Leontief production function, which state that two inputs are used in fixed proportion, and production function is represented by Q is equal to a minimum of KL, where Q represents output, K represents capital, and L represents labor. Isoquant of Leontief production function is L-shaped and the region above. The L-shaped isoquant curve is a convex set. Example 2. Any function on real number which rises monotonically until it reaches global maxima and then falls continuously, such as Q is equal to minus I raised to the power of 2 as concave function, as graph of this function will be in a bell shape, which states that for any I1 there will be I2. Analytical criteria for quasi-concave and quasi-convex. If f is a function on an open convex subset U of real number, then f is a quasi-concave on U if and only if fy is greater than equal to fx, implies dfx into y minus x is greater than equal to 0. And f is quasi-convex on U if and only if fy is less than equal to fx, implies dfx into y minus x is less than equal to 0. Now let us summarize what we have learnt in this module. Convexity function y is equal to fx, that is defined and continuous on interval x, is called convex if for any a and b from x and numbers q1 and q2 such that q1 plus q2 is equal to 1, q1 is greater than equal to 0, q2 is greater than equal to 0, we have that f bracket open q1a plus q2b is less than equal to q1fa plus q2fb. Concavity function is y is equal to fx, that is defined and continuous on interval x, is called concave if for any a and b from x and numbers q1 and q2 such that q1 plus q2 is equal to 1, q1 is greater than equal to 0, q2 is greater than equal to 0, we have that f q1a plus q2b is greater than equal to q1fa plus q2fb. There are three basic properties of concave function. The critical points represent global maxima, weighted sum of concave function is concave, the level sets just have the right shapes for consumption and production theory. The concave function represents global maxima, which is very important concept of economic theory. For example, profit maximization, cost minimization, utility maximization is only possible when these functions are concave. Homogeneous function, it is a functions that have multiplicative character. That is, if an argument is multiplied by a factor, then the result will be the sole power of the factor. Homothetic function, a function is called homothetic if it is a monotonic transformation of homogeneous function. Monotonic function implies more is better in the preferences. Convex set, A set U is convex set if whenever x and y are point in U, then every point on the line segment joining x to y is in U. There are three basic properties of concave function. The critical points represent global maxima, weighted sum of concave function is concave, the level sets just have the right shapes for consumption and production theory.